Monad is known to be particularly difficult among the topics related to functional programming. If you search for contents about monads, they each explain the concept in different ways. That's because it's a tough concept to pin down. To fully understand monads, we have to delve into category theory and study their challenging mathematical meanings. But what we need to understand for using monads in programming is not as difficult as you might think. After watching this video, you should be able to understand the content of other resources related to monads much more easily. If you're not familiar with functional programming, I'd recommend watching this video first. Let's get started then. A monad is a magic box which contains a certain value. For example, you can put data, like the number 2, into this magic box. These magical boxes each have their own uses and features, but they all have the common ability to accept magical spells that change their values. These spells are in the form of pure functions. For instance, you might write a spell that adds 3 to a given value and execute it in the box. When the box gets a spell, it produces a new box with a value that has been transformed by the pure function. So, in this case, a new magic box containing the value of 5 is created. Now, if we cast another magical spell on this box, this time one that multiplies the existing value by 4, it creates another new box, this one holding the value 20. Because the result is also a magic box of the same kind, we can continue to cast spells in form of pure functions, thus allowing us to perform a series of tasks. Those of you who have some experience with programming might think of method chaining at this point. Actually, up to this point, it's the functionality of functor, not monad. But for now, let's take a look at this part in code. You can check out the Notion page pinned in the comments for a link to example codes. The codes are written in JavaScript, so you can practice in the developer's tool. Let's take a look at our first example code. JavaScript arrays are not monads in the strict sense, but they have functionalities of monads, which makes them good intuitive examples. JavaScript arrays are also like the magic box we mentioned earlier. This array is a box containing the number 2, therefore there is a method called map in this instance, which can accept a spell written as a pure function like this. The map method returns another array as a result. Inside it, there is a new value created by the spell. Because the result returned by the map is also an array, you can use the map consecutively like this. By mapping a function that multiplies by 4 like this, you can get an array with 20 in it, and by mapping it with a function that divides by 5, you can get an array with 4 in it. We can say that data types with map or similar methods like JavaScript arrays have the characteristics of a functor. Java's stream, Python's list, C#'s IEnumerable, etc. fall into this category. But this is not enough to be called a monad. To be a monad, in addition to map, there should be a function called FlatMap. Let's examine this example. Among the pure functions that are mapped to the boxes, there can be functions that package the data into the respective box and export it. We will look into the reasons for using such functions later. This boxing function takes the provided data and returns it in an array. In other words, it's a function that packages the data and sends it out. Therefore, if you map this function to an array containing 2, it will return a nested array containing another array. The map sends out the results of a function in the box, so it ends up being double packaged like this. In the example we just saw, I modified one of the mapped functions like this. It's a function that returns an array containing 2 things, 4 times the given value and the value raised to the 4th power. Since a double array is returned at this stage, the next stage cannot divide by the integer 5, and thus an unintended result is produced, as you can see here. It's because when you open a box in the map process, it spells out an array instead of a number value, making division operations impossible. Therefore, these functions should be applied as a flat map, not as a map. Unlike the map, the flat map does not package the result of the given function, so there is no double packaging in such cases. Now, if you apply a function that returns an array in this way using FlatMap, you can see that it produces a normal result like this. Functions that return data itself are applied with map to send the result in a box, and functions that return a value already packed in a box are applied with FlatMap to prevent double wrapping. Data types such as JavaScript's array or Java's optional, which have a method called FlatMap, fundamentally possess the features of a monad. If it has the function corresponding to a map, it's called a functor. If it also has the function for a flat map, you can think of it as a monad. map and FlatMap are not always separately distinguished. JavaScript's promise is a good example of a monad, and it's okay if you don't know promise yet. This code puts the number 2 into a magic box called a promise, and use this then method to apply the functions to use like magic spells. The then method of the promise returns another promise, which is to say, a new box. This is similar to the functions of map and FlatMap. This function returns a number, that is, a normal value, not in the box, but these functions return the result of putting values into another promise box. This then method smartly handles both cases by using the map approach for functions that return a normal value and using the FlatMap approach for functions that return another promise. So, developers don't need to make the distinction between methods.
By the way, why do we use functions that package and ship in different boxes?
Magic boxes, named promise, are typically used for time-consuming asynchronous operations. For example, AJAX operations that fetch data from the network. Let's create a function that creates a promise that consumes 1 second. If you run it like this with 2 as an argument, a promise that returns 2 after a second will be created. If you put functions that return the same promise in the chaining of this then method, it sequentially consumes 1 second each, and as such, you can see the result printed out after a total of 3 seconds. Just like this, you can chain consecutive asynchronous tasks using method chaining.
If it were a language without something like promises, I guess I would have to write codes like this with callback hell.
That's true. JavaScript's async, await are also based on promise, so we couldn't use them. Anyway, whether it's synchronous or asynchronous operation, by connecting it as if it's synchronized using the then method in this way, you can conveniently write intuitive and readable code. You can see that Java's completable future and C#'s task are also monads that operate on similar principles, differing only in the names of their data types and methods, as well as whether they distinguish between map and FlatMap. Now, we will create the maybe class, another usage of the monad, directly in JavaScript. If promise was a kind of time capsule box, maybe is like Schrödinger's box. In other words, it is used to hold a value that may or may not exist, just like the types called option, optional, nullable in other languages. Such monads allow for the safe and convenient handling of operations when a valid value has not been returned. Let's imagine performing such consecutive operations on a certain number. There's a step where we divide the number by a value called our y in the middle. If this y is a non-zero number, a proper value will be logged at the end. But if y is 0, there will be a problem. Of course, in JavaScript, infinity is returned, but let's assume that an error occurs as when dividing an integer by 0 in many other languages. Then, the operation doesn't proceed all the way to the end and the execution of the program is interrupted. Hence, we put this number in a box called maybe, so that even when there's a problem in the middle, the code execution can continue. Let's first look at the class declaration code. There are these 3 essentials in a monad: unit, map, and FlatMap. First, what's called unit, which wraps a given value in this box called a monad. This maybe class has written as 2 static methods named just and nothing. Earlier, the resolve method of the promise we looked at corresponds to this. If you want to put a valid value in the box, use this just method to assign the value to the value field. If there is a problem and a valid value does not come out, you assign null with this nothing method. In other words, this maybe monad can make a box with a value with just, or an empty box with nothing. The next feature is the functor function, commonly referred to as the map method. It carries out the given function and then puts the result back into a box. However, the map of this maybe would absolutely return an empty box if this box is empty, because no valid value can be made from nothing. Finally, there's the FlatMap, also known as bind. It's the same as the above map, but you can see that it doesn't wrap the value in the box when sending it out. These 3 are the essential elements of a monad. The rest are unique features of this maybe monad. The isNothing method returns whether this box is empty. getOrals returns the value in the box if it is there, and if not, it returns the value given as a parameter. Next, here's a function that safely performs division using this maybe. This function, when the second argument is not 0, packs the value obtained by dividing the first argument by the second argument into a maybe box, and in case the second argument is 0, it returns an empty maybe box.
It's a function that sends the result out inside a box, which is the target of FlatMap.
That's right. Now let's use these to do the serial numerical operation we saw earlier. First, we start by putting a value into a maybe box. We'll apply a series of given operations to this box using map or FlatMap. Since addition, multiplication, and subtraction functions are free from errors no matter what integers are given, apply the function that returns a value with map. But because division can cause an error when the denominator is 0, apply the safe divide function we just wrote with FlatMap. Doing so, if a non-zero value is given, the normal value is passed in the box until the end of the code and 3 is returned. However, if 0 is given as a denominator, the box becomes empty at this point. As I just wrote, the empty box continues to return an empty box in the subsequent map or FlatMap. However, the program does not terminate due to an error. And finally, the message contained in getOrals is printed out like this. Apart from promise and maybe that we looked at in this video, various monads can be made and used depending on their purpose. So, we can summarize monads like this. They are magic boxes that have the ability to hold a given value and later process the subsequent functions given by map or FlatMap, returning other boxes. If you remember just what I've shown in this video, you'll be able to understand other, more detailed contents about monads much more easily. In fact, knowing up this point is fine for using monads in programming, but I'll explain some additional laws that must be followed to classify something as a proper monad. I'm going to explain briefly in this video. First, it's the left unit law. When there's a certain value and a function, the rule is that the result of wrapping this value in a monad and applying a function should be the same as simply giving that value to the function. The next rule is the right unit law, which stipulates that the result of applying a function that simply returns the same value to the monad should be identical to the original monad.
Up to here, it just sounds like common sense.
Yes. The last principle is the law of associativity. When applying two functions f and g to a certain monad, applying g to the result of first applying f should yield the same result as applying a single function that is a combination of f and g sequentially. I've posted all these examples on the Notion page, linked in the pinned comment, so you'll be able to understand quickly if you take a look. This way, we explored the topic of monads, which isn't so easy to grasp. Many people struggle to understand this concept, but I hope this video helped. I'll see you in the next video then.